So we'll introduce the topic of double slit interference with a demonstration.
So this is a glass paperweight that I received from serving on the strategic planning committee when I lived in South Africa. So myself and about 10 other people agreed to or volunteered to be part of this committee, put in about 20 hours where we came to a conclusion, made a recommendation to the superintendent, which he then disregarded. And for all of our hard efforts, this is what we received. Okay, a paperweight of Africa. And just as I was about to throw this in the trash can, because I mean, how many paperweights does a person need? I thought, what can you do with something like this? And I thought, I know. It's a great way to demonstrate the interference of light waves. So that's what we're going to show you here. Okay, we're going to place this glass paperweight down. We're going to shine a laser through it. Okay, and you are going to get to see interference of light waves. When you're looking at the screen, you will notice that even though light is shining through this piece of glass, there are going to be alternating patterns of light and dark. So these light waves will be destructively interfering to produce dark spots at certain points on the screen. Now you see the laser light shining through this beautiful glass paperweight. And you'll notice that you see an interference pattern. If you look at the pattern you see on the screen, you'll notice that there are dark spots or dark fringes which correspond to complete destructive interference of the light rays. You'll also notice that there are bright spots, but some spots actually appear brighter than others. Those super bright spots would correspond to the constructive interference of these monochromatic light rays.
So in trying to answer the question, what causes the formation of the light and dark fringes that you see on the screen? It turns out that the ray model of light that we used in our discussion of both reflection and refraction, that this model of light is inadequate, is insufficient to explain the phenomenon that we just observed in this video clip. So it turns out that when we're dealing with topics like the reflection of light and the refraction of light, okay, the field of geometric optics, then the ray model of light was sufficient to be able to explain both of these phenomena. But we're now entering the field of wave optics, where we want to be able to explain today the interference of light, and next week we'll talk about the diffraction of light as well as the polarization of light. And it turns out that to explain these phenomena, the ray model is not adequate. It does not work. So we can say here that we need a new model. Okay, the limitations of geometric optics, okay, prompts the need for a new model to explain phenomena in wave optics. And I say here the ray model fails to account for the true wave nature of light when light is allowed to pass through small openings or pass around objects. Whenever the wavelength of light is on the order of either the dimension of the opening or the object, okay, that the light is passing around, when this criterion is met, okay, it turns out that we need a more sophisticated model. This is what we call the wave model of light. In this slide, we'll talk about restrictions on or conditions for our light sources that lead to interference. So we will introduce some vocabulary that will be needed to describe these sources of light that lead to light interference. So let's take a look here. We'll start by talking about the difference between coherent light sources and incoherent light sources. Two wave sources are coherent when waves emitted from each source maintain a constant phase difference with respect to each other. In other words, the waves are not emitted at random times. Examples of such sources, if you look at sound waves, for example, sound waves are emitted from two speakers that are driven by a single amplifier. Okay, would be an example of, okay, a coherent wave source. When we talk about light, we say light emerging from two slits produced by a single monochromatic source. We'll describe what a monochromatic source is in a bit here. So this would be an example of a coherent light source, and this is what we'll see in the classic Young's double slit experiment that we will introduce in the next slide. You can reason then that an incoherent light source would be, where two wave sources we'd say would be incoherent when waves emitted from each source do not maintain a constant phase with respect to each other, such that the waves can be emitted at random times. Examples of this, a classic example would be light that is emitted from an incandescent bulb. So these light sources would be considered incoherent. When we talk about a monochromatic light source, we're talking about a source that produces a single wavelength of light. So the most common example here for light is that of a laser. We can also create a monochromatic source by taking light of many wavelengths and then filtering it. So if we look at light that's emitted from a spectrum tube, that gets excited by an electric current per se, for example, like what you would find in a neon sign, and then filter it so that only a single wavelength of light is coming through. That would also represent an example of a monochromatic source. So basically we can say this, that the conditions for interference, light waves will interfere when the wave sources are both coherent and monochromatic. And it turns out that laser light meets both of these conditions. Light that is emitted from a laser is both monochromatic as well as coherent. The rest of today's lesson will be devoted to a specific case involving the interference of light waves. And this is the classic double slit interference first described by Thomas Young in the early 1800s. So let's start by taking a look at the setup of his experiment as well as the interference pattern produced. So what you see on your screen here is a simulation of the Young's double slit experiment. And we start here on the left-hand side by noting that we have a monochromatic incoherent light source, like what would be produced with a laser. And you may actually, if you look at your notes, I think I included a collimator. You might use a collimator because this could take a beam which of diverging light from a point source, and you can use a collimator to change this diverging light pattern into a narrow parallel beam of light. So that's the end result we see here on the left of our screen. Notice that it is aimed at our two slits. Our two slits are not only narrow, they're not only thin, but they're fairly close together as well. So we can talk about the slit separation or slit spacing as well as the slit width. Both of these dimensions will come into play. We have our viewing screen, and the viewing screen should be very far away in comparison to the slit dimensions. And you see here on the screen we have this alternating pattern of light and dark fringes. They get produced on the screen. This is our interference pattern. So this simulation nicely shows the these fringes being formed. In the next slide, we'll actually take a look at a real-time demonstration of this setup and the interference pattern produced.
All right, so what we have here, folks, is the classic Young's double slit experiment. And looking at the setup of this experiment, you see that we have a helium neon laser which we're allowing to shine through a couple of very closely spaced parallel slits, which you can't really see, it's too small for the naked eye, but okay, this laser light is shining through these very closely spaced slits. Now, what we're saying is that, well, first of all, the light that is coming from the laser is what we call monochromatic and coherent, which means that basically when the light enters those slits, those light rays we can think of as being in phase with each other. Okay, so if right when one ray enters the left-hand slit, okay, it's right at a crest of a wave, we can assume that it's also going to be at the crest of a wave, okay, for the ray that enters the right-hand slit. So when these rays actually travel a distance across the room and hit the screen and interfere with each other, and recall, when we talk about wave interference, we're saying what happens when two waves encounter the same region of space at the same time. Okay, so when it turns out that these waves interfere with each other, okay, we end up getting this interference pattern. Okay, we end up getting these waves to constructively interfere at some locations and destructively interfere at other locations. And because we're talking about light waves here, we will see constructive interference as a bright spot, okay, in that region, and destructive interference as a dark spot. So the bottom line is that you can shine two rays of light, okay, and that they can cancel each other and produce darkness. So in a second here, we are going to have to darken the room, and we're going to change the view of the camera so we're looking at the screen, and we'll check out this interference pattern that we see.
So you see here how we have the central bright fringe, okay, that is surrounded on either side by these dark bands or dark fringes, okay, there and there. And this pattern of alternating bright and dark fringes continues outwards in the horizontal direction. So this is the interference pattern that we want to see if we can explain using a wave model for light. In this slide, we'll take a look at the conditions that lead to both constructive and destructive interference. In other words, what causes these bright fringes and dark fringes? So, we'll start out by taking a look at this figure here where you see Young's double slit setup. Okay, you see your two slits and you see your viewing screen, and obviously this is not drawn to scale. We have slit S1 and slit S2, and the wave that is emitted from slit S1 travels a distance R1 to the viewing screen, whereas the wave emitted from slit S2 travels a different distance, or possibly a different distance, R2 to the viewing screen, okay, before they interfere at this arbitrary point P. So we're just looking at this arbitrary point where these two waves will meet and interfere with each other. So we make this approximation that when L, that is the distance between the slits in the viewing screen, is much, much greater than D, that is the slit spacing, the distance between two slits, then these two paths here, R1 and R2, okay, become parallel rays. Now, obviously, I can't show you this in the figure here. I can't show you this to scale because the slide is not wide enough, right? But I want you to imagine this, that in the real-time experiment I showed you of Young's double slit interference, the distance between the slits in the viewing screen was many meters, whereas typically the distance between two slits is on the order of millimeters or even fractions of millimeters. So in that case, this approximation is very good, in which case, okay, our picture is going to look something like this. Okay, that R1, that is the distance or the path that, okay, the wave takes that's emanating from slit S1, okay, will be parallel to the path R2, okay, which is the path that the wave emanating from slit S2 takes before reaching the viewing screen. So when you look at these figures here, okay, we talk about the path length difference del, and this is a concept that we introduced previously. All right, this is the difference in path length between the two waves, okay, in the journey they take to the screen. So what we're saying here is that the wave that is emitted from the slit S2 travels a further distance to the screen, okay, at least to point P, than the wave that is emitted from slit S1. And that this distance del represents the difference in distance traveled, okay, between these two waves. And using so here's, the difference R2 minus R1 is what we call del, which is the path length difference, in our case, an optical path length difference. Using a little bit of right triangle trigonometry, you can see here that this distance here, del, this length del, is one side of this right triangle here, which is just d times the sine of theta. And d, recall, is the distance between the two slits. So, okay, we are now in a position to write down our interference conditions. So I want you to think about it. And we'll start with a case of constructive interference here. Okay. If there was no difference in distance between the wave emitted from slit S1 and slit S2, and if both of these waves start out in phase, okay, remember the conditions for light interference, this means that these waves emanating from both slits are both monochromatic and coherent, right? Monochromatic means same wavelength, coherent meaning that, okay, they are always in phase with each other. They're not being emitted at random times. So we're saying that for a monochromatic coherent source of light emitted from S1 and S2, if there was no difference in optical path length, no difference in the distance traveled to the screen, since these waves start out in phase and maintain that phase relationship, then they will constructively interfere. Okay, when they reach the viewing screen, crests will meet crests, so you'll get constructive interference. Okay, I want you to now imagine what would happen if the wave traveling from the bottom slit traveled exactly one wavelength further than the wave emitted from the top slit, okay, before reaching point P on the screen. In that case, okay, you would still have these waves reaching the screen in phase. Okay, you would still have crests lining up with crests, in which case you would still have the condition for constructive interference. If the wave traveling from the bottom slit to the screen traveled exactly 2 wavelengths further than the wave emitted from the top slit, they would still be in phase when reaching the screen, and in which case they would still constructively interfere. So hopefully you would agree that we can write a general condition for constructive interference as follows. Okay, saying that the difference in distance traveled to the screen, the difference in optical path length d sine theta, okay, it could be 0, in which case they're in phase, or it can be an integral number of wavelengths, like 1 wavelength, 2 wavelengths, and so on. So this is our general condition. Notice that we put the plus or minus sign here, because when you look at our picture here, and this angle theta here, which using a little bit of trigonometry is exactly identical, this angle theta, notice that we get fringes on either side of the center. So in a sense, theta could be, have a positive value, let's say, if it's upwards, and a negative value if it's downwards, or, okay, so we use the plus or minus notation to indicate, okay, the two, possibilities. We could have really, the same magnitude of theta, but on 2 different sides of, okay, our center line here. Likewise, we can write down a condition for destructive interference. Okay, you can imagine, and we'll go through this a little bit faster, that if The light wave emitted from the bottom slit traveled exactly 1/2 wavelength further than that emitted from the top slit before reaching the viewing screen. Then you would have a crest meeting a trough. You would get complete destructive interference at the screen. Likewise, if the difference in path length was not just 1/2, but if it was 1.5, 2.5, 3.5 wavelengths, the same condition would be met where you would have complete destructive interference. So we can write our generalized destructive interference condition as follows, saying that the difference in optical path length, the difference in distance traveled, okay, between the wave that is emitted from the top slit and bottom slit, okay, d sine theta, if it is, okay, half a wavelength, 1.5 wavelengths, 2.5 wavelengths, and so on, okay, then that would be the condition for destructive interference, which we can write as follows. And you'll see here that m, which we call the order number, when n takes down on a value of 0, the difference in path length is 1/2 a wavelength. When n takes a value of 1, let's say, it's 1.5, 2, 2.5, and so on. So in the next couple slides, we'll take a look at the relationship between d, the slit spacing, and theta, which is a measure of the angular separation of these fringes on the screen. So in this slide, we'll look at a simulation which nicely shows this relationship. Notice here as d is increasing right now, okay, notice that theta is decreasing. In other words, as the slit spacing gets bigger, the angular spacing between these fringes gets smaller. There's an inverse relationship between slit spacing and, okay, the distance between these fringes on the screen. All right, so in this slide, I've created a simulation which will also explore this relationship here, and we can slow this down since we're going to be looking at some still shots here. So first case we'll look at is what happens when the slits are fairly close together, when there's a small slit spacing. What I'm showing you here is the wave front, okay, the wave that is emitted from the top slit. All right, and you'll notice here that there is the wavelength is represented by the distance, okay, between two wave fronts. So since we're talking about monochromatic coherent sources, notice that the wave that is emitted from our bottom slit here, okay, has exactly the same wavelength. And you'll notice you can see these bands here where you can see these regions of the constructive interference where the crests line up and the troughs line up. So I'll show you with these bands right here. Okay, so notice the angular separation of those bands, those regions of constructive interference, when the waves emitted are pretty close together, suggesting a small slit spacing. Let's now take a look at the case corresponding to a larger slit spacing. So once again, we have the wave that is emitted from the top slit, okay, the wave emitted from the bottom slit, and you can clearly see the greater distance, okay, between them. And once again, it becomes a little bit harder, but if you look carefully at the screen, you can still see those regions of constructive and destructive interference. I will show you with these bands here, okay, some of them. And you'll notice what happens here, right? Slit spacing increases, the angular separation of those bands on the screen, the regions of the constructive interference, decreases. So we have this inverse relationship between slit spacing and the separation distance of our fringes on the screen. So how do we identify these particular fringes in this Young's double slit experiment? Well, we come up with a naming system. And there's really no physics here, but you have to recognize the vocabulary because it can lead to a source of confusion in the problems. So I'll explain in a second. The fringes are named according to the order number, that is the value for M. So let's look at some examples here. When we talk about the zero order maximum, in other words, when M has a value of 0, this is what gives us the central bright fringe, okay, when theta has a value of 0, the central bright fringe on the screen. Okay, this is what we call the 0th order maximum. The 0th order minimum corresponds to a value of m equals 0 as well. Okay, and this gives us the dark fringe on either side of the central maximum. So remember that, okay, from our viewing screen, we really get two fringes, two dark fringes with the same angular separation, okay, one on each side of that central bright fringe. When we talk about our first order maximum, that corresponds to the value of m equals plus or minus 1. Okay, so we're talking about the bright fringe on either side of the 0th order minimum. Okay, or this, we could said differently, this would be the bright fringe on either side of the central maximum. Okay, and then last example, look at the first order minimum would correspond to an order number of for m of plus or minus 1. This would identify the dark fringe on either side of the first order maximum. So a note of caution here, when you're dealing with problems on this, if you're given the order number, if the problem says order number, then that tells you the value for m. Okay, but if the position of a fringe, either a bright or dark fringe, is actually described, you have to be careful to figure out the corresponding order number, which means that you have to understand the naming system. Okay, so be careful, because some problems give you the order number, some problems just describe a particular fringe, in which case you have to then figure out the order number in order to solve the problem. So in this slide, we will take a look at how to describe the position of the fringes on the viewing screen. We will once again make this approximation. Remember that the diagram you see over here is certainly not drawn to scale. Just like we said before, L, the distance between the slits in the viewing screen, is many orders of magnitude bigger, okay, than the slit spacing. So that this approximation, all right, when theta is very small, we can say that the sine of the angle theta, okay, is approximated by the tangent of the angle theta. The fringe position in terms of this angle theta, okay, if we look at this diagram here, when we take the tangent of theta, and I'm looking at this right triangle here, I'm showing you with the laser pointer. Okay, when we look at this right triangle here, you'll notice that the tangent of this angle theta here, which is the opposite side over the adjacent side, that is y over L. All right, and we can solve for y, and y simply gives us the distance between the central bright fringe and any arbitrary fringe we choose to look at. So y gives us a measure of the distance to a particular fringe on the viewing screen from the center. So y is equal to L tan theta, and then we can use our approximation here, okay, to say that that is about equal to L sine theta for small theta. And this approximation works really well when theta is less than 10 degrees, and for most situations where you're setting up this double slit experiment, theta will be much less than 10 degrees. When L is on the order of many meters, and okay, D, we said this slit spacing is on the order of millimeters or fractions of millimeter, then that condition is clearly met. So we can also write the fringe position in terms of wavelength, okay, and we can use our interference conditions to do that. So for identifying the position of the bright fringes on the viewing screen, which we say is equal to L sine theta, remember that our constructive interference condition that gives us the bright fringes, we say that d sine theta is equal to m lambda. All right, in which case when you solve this equation for sine theta is equal to m lambda over d, And when we substitute that in for sine theta, we find that these positions on the viewing screen, the bright fringes, are given by this equation here, m times lambda times L over D. Okay, of course, m takes on these integral values. We can do the same for the dark fringes on the viewing screen. Okay, their positions are identified by L sine theta, where, using our condition for destructive interference, sine theta is equal to m plus 1/2 lambda over D. Okay, when we substitute that in here, we can locate the position of the dark fringes, okay, on the viewing screen on either side of the central bright fringe, that central maximum, okay, using this equation. Before applying the theory that we've introduced in solving various double slit interference problems, we're going to take a brief, but I think you'll find interesting diversion here to see what the double slit experiment has to inform us about the quantum world that we live in. Now, we introduced the wave-particle duality of light, the idea that we need both a wave model and a particle model if we want to describe the true nature of light. Okay, so in this slide, we're going to explore what happens when both waves and particles are aimed at our double slit grating. Okay, so we're going to start out by assuming that we're going to shoot classical particles at our two slits. And when I say classical particles, think spray paint, maybe think COVID-19, spit molecules, if you like. So what would you expect to see behind the viewing screen if you're going to shoot spray paint at these two slits? Well, I don't think the answer is going to be surprising. What you're going to see is you're going to see these little particles, these classical particles, forming a pattern directly behind those two slits. So wherever the slits are, directly behind them, where there's an opening, you're going to see the little particles on the screen. Certainly, the further the screen is away from the two slits, the greater the divergence, or the wider the pattern will be. Yet, those, I shouldn't call them fringes, those lines you will see on the viewing screen will be directly behind the slit. So, as Bongo will nicely tell us here, as expected, you're going to see particles of spray paint directly behind the open slits. All right, in our second experiment, we are going to shoot classical waves at the slit. And this is pretty much what we've been talking about thus far in our presentation. So let's suppose you want to shoot light at the two slits. Well, we know what we're going to see. That's what we've been talking about. Young's double slit experiment tells us that when you shoot light at your two slits, you're going to see an interference pattern consisting of both light and dark fringes, on the screen. Regions where we get both constructive and destructive interference. So as Bongo says here, as a result of wave interference, you're going to see a series of bright and dark fringes. Young's double slit experiment offers definitive proof that light behaves as a wave. So think about this. Particles do not interfere. You cannot shoot two particles at a screen and get a dark spot, because particles don't interfere. In order to describe this interference pattern where you see these bright and dark fringes, you must use a wave model, in order to explain this. All right. So now let's take a look at what would happen in the next experiment if you were to shoot electrons. Particles, you may think, but little, very tiny ones, much tinier than droplets of spray paint. Now, in the first experiment here, our first trial, one of those slits is closed. So what happens when the right-hand slit is closed and you shoot electrons at these two slits? Well, what you're going to see here is exactly what you see in the case of the spray paint, in the classical particle experiment we conducted above. You're going to see, a pattern, okay, directly behind that open slit on the screen. And as Bongo's saying here, with one slit closed, the electrons know to behave like classical particles. Okay, and the pattern is just like that of the spray paint. So that may not surprise you. All right, okay, get ready to for something amazing here though. All right, and that is our very last experiment. What happens if we do the same thing? We shoot electrons at our two slits, but in the second trial, both slits are now open. What are you going to see? Well, when this is actually done, okay, and this isn't just a thought experiment. I mean, we may be treating it as such, but this can be done. And what you find is that you get the interference pattern, okay, which suggests that when both slits are open, those electrons are behaving as waves. Okay, in one case, the electrons behave as particles. Okay, in the other case, they behave as waves. And if you're saying to yourself, okay, so here is the interesting part. Okay, well, and let's review here. As Bond was saying, with both slits open, the electrons behave like waves. Here is the inescapable quantum paradox. If an electron is a particle, then it must pass through either one slit or the other. Okay, which would force you to conclude that that electron somehow knows about, is somehow aware of the state of the other slit it doesn't pass through. Okay, think about it. Okay, if electrons weren't conscious, how would they know what type of pattern to produce? What we're saying here is that if an electron is going through the left-hand slit, okay, it somehow knows whether the slit it doesn't pass through, the right-hand slit, is open or closed. Because if the right-hand slit is closed, then the electron behaves one way. It behaves as a particle. But when that right-hand slit is open, now that electron behaves in a very different way. It behaves as a wave to produce an interference pattern. I'll say here to finish up Bongo's thought here, perhaps the electron travels through both slits at the same time. Okay, something interesting to ponder about. And if you're saying that this bothers you, well, you're in good company. Believe me, there's a lot of great scientists, okay, with great minds who are equally bothered by this quantum paradox that is proposed in this double slit experiment. All right, so after that little diversion, we will now return to the theory that we've been talking about and apply it in solving a typical Young's double slit problem. So in this problem here, we're going to use some double slit interference data to actually determine the wavelength of light. And believe it or not, this is a lab that we typically conduct in Physics 102, okay, actually collecting data and using it to determine the wavelength of light. So here we're told that a pair of narrow slits are 0.075 millimeters apart, okay, are located 1.5 meters from a screen. Laser light shining through the slits produces an interference pattern whose third order bright fringe is 3.8 centimeters from the screen center. And from this data, we're asked to find the wavelength of light. All right, so with this problem, with any problem, we're going to start by writing down what kind of information we're given in the problem, okay, what kind of data we're given. So let's start by doing that. And here we have, notice when it says third order bright fringe, okay, that is the order number m. Okay, that is given to us. Okay, so we know that m equals 3. I want to point out again that there is a difference between the order of a fringe and the fringe itself. So in this problem, it states third order, in which case you know m equals 3, because m represents or means the order number. But what if, for example, the problem had said the first dark fringe? Okay, in that case, you would have to know that the first dark fringe on either side of that central maximum corresponds to a value of m equals 0. Okay, so again, you have to understand this naming system. And when you're given an m value, you have to know, okay, what fringe that corresponds to. Anyways, getting back to this problem here, L, the distance between the slits in the viewing screen, is 1.5 meters. D, the slit spacing, is given to us as 0.075 millimeters, which I've converted to meters. In wide bright, that is the distance between the center of our viewing screen and the third order bright fringe is 3.8 centimeters, which I've converted to meters. Be careful here. Notice that, LD and wide bright, these are all distances. They are typically all given different units using different metric prefixes because they're different magnitudes. So whenever you do a problem like this, most likely you're going to have to convert units. So given this, we can use the theory that we've developed. We said that if we're talking about bright fringes, we're talking about constructive interference here. So this relationship tells us, okay, the bright fringe distances, the distances of the bright fringe from the screen center, okay, and here we want to solve this for wavelength, so we'll solve it for lambda, and then we're just going to plug in our values here. Plug in our value for wide bright, the 0.038 meters, the value for D, the slit spacing, okay, M, our order number is 3, and the screen distance of 1.5 meters. And when we do that, okay, we come up with the number 633 nanometers. Well, I guess it was initially in meters. We converted it to that. Just want to point out here that this is the wavelength of red light, okay, from a low-powered helium neon laser that is commonly used in physics laboratories. So you can see here that by conducting this double slit experiment from its data, we can very accurately determine the wavelength of light. So we're going to finish today's lesson, okay, really the next 4 slides, by taking a look at the intensity distribution of the double slit diffraction pattern. Okay, and here's the problem that we're going to confront. Okay, first of all, I never like to have a physical law magically appear on the screen. I always like to show the physics behind where it comes from. The problem is that to truly understand what we'll be deriving in these next few slides, you would need to know a lot more about electric fields, okay, than you probably do, because this is a topic that we don't introduce until you get to Physics 103. So I'm going to go through the derivation in the next few slides. Okay, try to follow along. A lot of it is going to be review. Okay, some of it won't. And in case you're wondering, okay, this derivation will not be on the test. So let's get going here. I'm going to start by saying that, what are we trying to do here? Note that the bright fringes get fuzzy around the edges, suggesting that the light intensity for a given fringe is not constant. And I just want to point out here, if you look at the brightness of a given fringe, the fringes in the Young's double slit interference pattern are equally bright. In other words, you can say that the first order fringe is as bright as a second order fringe. But within a given fringe, you'll notice that the center of the fringe is very bright, but then it gets a little bit dimmer as you move away from the center, suggesting that the intensity changes for any given fringe. And that's what we're trying to do in the slide. We're trying to see how the intensity, how the brightness changes for a given fringe as you move, horizontally, okay, from the center of the fringe. So in order to do this derivation, we're going to start by reviewing some facts about electromagnetic waves. So this is where I'm sure everybody remembers this. We say that electromagnetic waves are created by accelerating charged particles. We've said it before, very important, so we'll say it again. And an electromagnetic wave can be described by its combination of electric and magnetic field vectors. Remember, what is an electromagnetic wave? It is nothing more than this oscillating pattern of electric and magnetic field vectors. Okay, so we're going to describe the amplitude of the electric field vectors for a coherent electromagnetic wave, okay, or I should say waves emitted from slits S1 and S2. So if we take a look at describing the electric field emitted from slit S1, we can do it as follows. We can say it's equal to E naught. E naught represents the amplitude of the electric field times the sine of omega t. Notice that we're making this sine omega t, from what we know about wave theory, that represents a wave, okay? E naught the amplitude. So, no surprise here, this electric field is wave-like, because what we just said is that's what an electromagnetic wave is. It is a combination of both an electric and magnetic field vector which behaves as a wave. We can likewise describe the electric field of the wave emitted from slit 2 as follows. Okay, E naught sine omega t plus phi. Once again, it looks wave-like. It has the same amplitude as the wave and electric field for the wave emitted from slit S1. Okay, the only difference between these two is this phase difference phi. And I just want to point out that when we talk about a coherent source of light, okay, we're saying that the waves emitted from these two slits must maintain a constant phase difference with respect to each other. Okay, so as they travel here, and as you can see, phi is that phase difference. It is the only difference between these two waves. There is a relationship between the phase difference, okay, between these two waves and a path length difference. If we say that one wave travels a different distance before reaching the viewing screen than the other wave. And this is something that we've talked about before. We can correlate a phase difference with a path length difference. So I'm saying that a phase difference, I call it delta phi, okay, divided by a path length difference, delta r, must be equal to this ratio, okay, 2 pi radians over one wavelength. So in other words, saying that there's a path length difference of one wavelength is completely equivalent to saying that, okay, these two waves are 2 pi radians out of phase with each other. And in this case, we're talking about the electric fields, okay, of these two waves. So we can take this and we can solve this for delta phi, okay, and we can write it like this. Okay, the delta phi is equal to 2 pi radians over lambda times the path length difference, R2 minus R1, which, recall from, specifically for our double slit experiment, the path length difference we showed is equal to d sine theta when we make this approximation that the viewing screen is very much, that distance is much greater than the slit separation. Okay, so that these rays coming from the two slits we can consider to be parallel rays. So let's continue on here. We need to find an expression for the resultant electric field using the principle of superposition. Remember, saying that these waves interfere, okay, then we use the principle of superposition, which says that the interference pattern is simply the sum of the individual waves. So basically, we just got to add up, okay, the electric field of the two waves that are emitted from each of these two slits. Okay, so this is nothing new. We're adding up these two waves representing the electric field, okay, for the light sources emitted from each of these two slits, and we can use a trig identity here, one we've seen before, to simplify this expression when we add these two sine functions here, okay, with different arguments. So this is a trig identity that we've used before when we talked about the interference pattern for traveling wave interference, okay, many weeks ago. And when we use this trig identity, our interference pattern looks like this. Okay. So here is what our interference pattern looks like. Okay, this expression here. I won't read it to you, but let's take a look. Okay, and since cosine is an even function, we can write it without the negative sign. Cosine negative phi is equal to cosine phi. So make that simplification here. So some things to note about the resultant field. Okay, that is the sum of the two fields. First of all, the frequency of the resultant field is exactly the same as the frequency of each of the waves that is emitted from the slits. Notice that each of those waves has a frequency omega. Also notice that the resultant field has a frequency omega. No surprise there. The amplitude of the resultant field has been changed, whereas the field of each of those waves emitted from the slit was E naught. Okay, notice that when we look at the amplitude of the resultant field here, okay, it goes from E naught to 2 E naught cosine phi over 2. So this then tells us that we get our interference conditions here. Okay, for the case of constructive interference, all right, when phi, this angle is equal to 2n times pi, n taking on these whole number values. So in other words, when phi is 0, okay, pi, 2 pi, 3 pi, then the cosine of 0, pi, 2 pi, 3 pi gives us either plus or minus 1, okay, in which case the magnitude of this resultant field goes like 2 E naught, okay, this is where we get constructive interference, all right, times, okay, the sine of omega t. And likewise, the case of destructive interference, when, okay, we look at this cosine phi over 2 term here, when phi is, okay, either, okay, 1 pi, so we're ending up with pi over 2, okay, 3 pi over 2, 5 pi over 2. For those values of phi, okay, the cosine of those values is 0, in which case we get the condition for destructive interference. All right, so the electric field sum is 0. All right, so we're getting there. So how do we go from electric field to wave intensity? And here's the part where, you know, if you haven't had Physics 103, there's going to be a little bit of a leap of faith here, but I don't think it's going to be too big of a stretch if you consider what you know about the intensity of mechanical waves. So recall back when we were talking about sound, okay, eons ago, where we came up with a model for the intensity of a sound wave, and we really had two models. We could express sound wave intensity in terms of, okay, a displacement wave or a pressure wave, and we showed that the intensity was directly proportional to the square of either the displacement amplitude, S max, or the pressure amplitude, delta P max. Now, given that, I don't think it's going to be too big of a stretch of the imagination to say, well, how do we go from mechanical waves to electromagnetic waves, and to realize that the intensity of an electromagnetic wave, okay, at a given point would be directly proportional to the square of the electric field, okay, at that point. So, and I know a little bit of a jump there, okay, I'm just going to have to believe me on this one, but once you know, okay, take that leap of faith, then everything else should fall into line here. So we're going to say that the intensity goes like, of an electromagnetic wave, goes like the square of the electric field at a given point. I should say the intensity of a wave at a point in space goes like the electric field at that point in space squared. So we have an expression on the previous slide for the net electric field that is emitted from those two slits, right? The sum of the two electric field vectors looked like this, so we're just going to square that. When we do that, we'll square, okay, you know, both of these factors, 2e naught squared gives us 4e naught squared, cosine phi over 2 gives us cosine squared phi over 2, and the sine function, we square that as well. Nothing surprising here. So we now want to talk about the average light intensity. And here we need, this is just a mathematical problem here. The average light intensity, if we look at light intensity, okay, averaged over time, and we look at this expression here that we derived, okay, well, 4E naught squared, that's a constant, that doesn't change, okay, cos squared phi over 2. Notice here that, okay, the sine function here, this does change in time. This shows the change of the electric field vectors and magnetic field vectors, although we're not talking about those here, how they change in time. And you'll notice here that if sine of theta oscillates between -1 and +1, the sine squared of theta oscillates between 0 and 1. And when we take the average value of sine squared, okay, between 0 and 1, the average value is exactly 1/2. So that's how we can replace this term right here, sine squared, okay, of the argument with this value of 1/2. It's a time averaged value. So given that, okay, our expression now looks like, okay, we take half of 4E naught squared, 2E naught squared, cos squared phi over 2. All right. So we can write this 2E naught squared really represents the amplitude, okay, of our average intensity. We'll call that I max. And now we're starting to get somewhere, okay? We're kind of seeing how the intensity of our, okay, double slit interference pattern, okay, we see how it has this angular dependence. It, okay, depends on, okay, the angle phi here. So in this slide, we will put forth the finishing touches so that we can see what this intensity distribution looks like for the two slit interference pattern. And on our previous slide, we left off, we have an expression for the average light intensity in terms of the phase difference between the waves emitted from these two slits. The phase difference expresses the angle phi. But what we would like is we would like to get an expression for the average light intensity as a function of, okay, either angular separation theta or, okay, fringe spacing on the screen, okay, the distance between our fringes here. So to do that, we will use this fact that we derived or showed a few slides ago, okay, that will convert a phase difference into this path length difference. Okay, so you remember this from a few slides ago, and we can now substitute that into our expression for average light intensity. All right, so we'll substitute in for phi, this path length difference, 2 pi over lambda times d sine theta. And so now you have an expression here for the intensity of a fringe, the light intensity, the average light intensity, okay, in terms of this expression here, theta, which is a measure of the separation distance of these two fringes. So we're going to look at a graph of this average light intensity versus not theta, but say the sine of theta, and we will see that it looks like this. Okay, I want to point out here that notice here that when the argument here of this cosine squared term, when d sine theta is equal to m times lambda, remember that is a condition for constructive interference. So let's do this in our head. If d sine theta is equal to m times lambda, then we get pi times m times lambda divided by lambda. We get pi times m, where m takes on an integral value. So in other words, we get cosine squared of, okay, 0, pi, 2 pi, 3 pi. So there, cosine squared of of pi of these values for the argument will be 1. Okay, this will be the maximum value of that cosine squared function. In which case, when d sine theta is equal to 1 lambda, 2 lambda, 3 lambda, or 4 lambda, that corresponds to the maximum light intensity, or the case for complete constructive interference. So notice that is where we see our peaks here, okay, for these the light intensity of these fringes. So if I'm looking at a given fringe, like if we look at the fringe right in the center of our screen here, you'll notice that there is a peak, a maximum, exactly when that condition for a complete constructive interference holds. But then you'll notice that as we move, let's say, on one side of that maximum, you'll notice that the intensity drops off. Okay, until we get to the case here, halfway between 0 and lambda, 1/2 lambda, this corresponds to no light intensity. That is going to be the first dark fringe, okay, on either side of, okay, our bright fringe here. And you'll notice here that when that corresponds to the case where d sine theta is equal to m plus 1/2 times lambda. That's going to give you complete destructive interference, or a dark fringe. Notice here that when I get to this next maximum here, this corresponds to the next bright spot, okay, where d sine theta is equal to not 0 lambda, but 1 times lambda here. So again, we get the case of complete constructive interference, we get this bright spot. So you'll notice here that while each fringe, there's a bright spot on each fringe here, which I'm trying to show you with this pattern, and then as you move a little bit on either side of the fringe, it gets dimmer, dimmer, dimmer until you get to the case of the dark fringe here, which also has, it's not as if it's just black or white. It's not just dark, right? It's extremely dark when we have complete destructive interference right in the middle, but as we move on either side of that, okay, it starts to appear light again. Notice that each of these fringes in the case of double slit interference is equally bright, okay, that the 0th order and the 1st order fringe, okay, the maximum light intensity or the maximum brightness is exactly the same for, okay, those two fringes as for all the fringes. So this function here describes this changing intensity pattern for, okay, the fringes that we see on the screen. Took us a little bit to get there, but okay, now that we're there, you can see how okay, the brightness of these fringes is not constant, okay, but it changes with position d sine theta on the screen.